This is the second lecture I record on variability and interdependability. Again, here we assume that our distributions are all discrete uniform. So demand comes in, there is a waiting line here, and then a station 1. If capacity is available here, what has come in goes to station 1. If capacity is not available, waits in the line. At the end of the day, if capacity was greater than or equal to demand, everything passes. But the gap between capacity and demand is lost. So if capacity is strictly greater than demand, the additional capacity cannot be used to build product for inventory. That capacity is gone, but if the demand is more than capacity, it can wait for the next day or the day after that. Then these orders go to another potential waiting line, and then go to station 2, and then go out. This is how the process works, and I would like to show you the impact of interdependability. I first assume both demand and capacity are coming from uniform 1 and 9. That is discrete uniform between 1 and 9. This is the demand. This is capacity of station 1 between 1 and 9. And this is capacity of station 2 between 1 and 9. When the demand comes in, if there is a demand in the previous day, that would be what is available for production today. And then here is capacity. If capacity is greater than available demand, we produce what it is and send it to the next station. But if capacity is less, the difference will stay in the line. For production of station 1, I have capacity of station 1, and then the demand for this capacity, which is what has come in today plus what was waiting in the previous days. And what I produce is the minimum of these two. I think we are all fine on this. And then what is left in front of station 1? What was there the day before, plus what came in today, minus what was produced. We had 0 in front of this station, 2 came in, capacity was 6, therefore we send out all the 2 units, and the rest of the capacity is vanished. We cannot produce for inventory under this assumption. You can develop a next model when you can also put there the assumptions that whatever capacity is left, you can produce and leave it for future days. The same is true for station 2. In station 2, again, capacity is uniform 1 and 9. Production is what is in front of this station the day before or from days before, plus what was produced in station 1 today, and then we compare summation of these two with capacity. If capacity is less than summation of these two we produce to capacity, if it is greater than that, we produce what is available and the rest of the capacity is gone. Again, you may make different assumptions and develop different simulation models in Excel. Production of final product, which is output of station 2, is equal to minimum of capacity of station 2 and what has been produced in station 1 plus what was waiting in front of station 2 from the previous days. And that is our production. Production of station 1 was 3. Capacity of station 2 is 1. Left in front of station 2 in the previous day is 0. 0 plus 3 is 3. But capacity is 1. We produce 1 and 2 units are left for tomorrow to be produced. So that is production of station 2 was equal to minimum of capacity of station 2 and demand for station 2, which was what was left in previous days plus what came in today, and that is production. But what will be left in front of this station is equal to what was left from previous days plus production of station 1 minus production of station 2. What we can do, can just take these numbers here and copy them all down. As you can see, because capacity and demand have the same average, system is quite unstable. That is why no system can perform at capacity, because waiting line will significantly goes up. Before talking about utilization and variability and their impact on these waiting lines, let me quickly talk about descriptive statistics. Whatever we do, we need to prepare some descriptive statistics. Data analysis, descriptive statistics, and then I will give this range demand. That is my descriptive statistics. And I ask to create summary statistics. Says, do you want me to paste it in a different workbook? No, please paste it here. This is descriptive statistic. But why I don't like it? Forget these parts, because these parts I have generated myself. Descriptive statistic is here. It is related to this column. And why I don't like it? I don't like it because it is not dynamic. It was for the first set of data that I used over there. And as soon as I paste it, because these data changed, these numbers are not valid anymore. So what I will do, instead of relying on that utility, which is available in Excel, I go here and type equal to average of what? Average of here to here, which is my average demand, correct? This is my average demand. Then I also make something, I'll say from 3 to 1002. Please note that here I have created 10,000 rows, but I have hidden it. So that is average of those numbers. I locked the number, but not the letter. I have it here. Now if I copy this down, it still refers to those set of data, but it's average. I remove average, STD, deviation of sample, and that is standard deviation of sample. This here, I don't need that many decimal points. Before copying down, I like to add something here, and that is coefficient of variations. Coefficient of variations lets me know how much variability do I have, which is a standard deviation, relative to average. So that is coefficient of variations. Variation is about 53% of the average. Then I copy this one, copy, paste it, and instead of standard deviation, I double click on it and I type mode. I really don't need it. Standard deviation I have already computed. Oh, that was a standard error, which is a little bit different. I'll compute it later. This is standard deviation. Variance is simply standard deviation squared, so I don't need it. Kurtosis and skewness, I also don't need it. Maximum and minimum. Copy and paste. And instead of average, I type max. And I copy down mean, range here, max minus mean, range to median, which is something I have initiated myself with something like coefficient of variations, range divided by median. And then we have count, which is summation of these numbers. Because I don't want to mark the Control C, Control V, and then now what is the standard error, which I had it here. The standard error is simply equal to standard deviation divided by square root of count, and that is the standard deviation of the average. Decimal point. So it is a standard deviation of average, which is much smaller than the standard deviation of the sample. Standard deviation of average of the sample, standard deviation of each random variable in the sample, and this standard deviation is much smaller. How much smaller? That one divided by square root of count. And I like to remove this decimal point. Confidence interval, or simply CI, confidence interval, and 95% confidence interval. And confidence normal. What is your alpha? Because I'd like to have a 95% confidence interval, alpha would be 1 minus that, which is 0.05. What is your standard deviation? This is my standard deviation. What is the number of observations you have? Is this one. Indeed, it is used just to again compute the standard error inside of this function. So now I have 95% confidence level. The average of this data is between 95% confidence. The average of this data will be between this one and this one, upper control limit, and minus this one. So now we have everything. Why this is better than what I did by using data analysis, descriptive statistics? It is much better because not only when these data are changed, everything is updated, but more importantly, I can take these numbers and copy them to the right and get all other information. Throughput of this system was 4.89. Average inventory in this system, inventory in front of station 1 plus inventory in front of station 2, and that is average inventory. Summation of this one and this one, which is now 42. So on average, 42.36 units were waiting. What was throughput? Throughput is equal to production of station 3. Little's law is 100% valid when the inventory at the beginning is 0 and inventory at the end is 0. It is 100% valid if inventory at the beginning and inventory at the end are equal. Not zero, but equal. And it's very close to reality under any circumstances as long as the system is not very unstable. Therefore, here, I can assume this is throughput, this is inventory, and we know that our great Professor Liddell said throughput times flow time is equal to inventory. Therefore, flow time in this system is equal to inventory divided by throughput. 22 days, 22 and a half days, 24 days, 15 days, 31 days, 10 days, 9 days, 29 days. Quite high and quite variable. Why? Because system is not very stable. If we look at the performance of the system here, these are the number of loads waiting in front of station 1 and in front of station 2. Utilization, which is defined as demand divided by capacity, or throughput divided by capacity, is close to 1. And also variability is high because numbers are between 1 and 9. Average is 5. Standard deviation is about 9 minus 1 to the power of 2 divided by 12. That is 64 divided by 12. And that is something around 5.33. Coefficient of variation is equal to 5.33 divided by 5, greater than 1. We don't call it very high variability, but it is medium variability, and definitely it is not low variability. Now let's go and take another look at the system. The first thing I am going to do is I am going to increase the capacity to see what will happen to this graph. Let me go and increase capacity of station 1 from something between 1 and 9 to something between 1 and 19 with average of 10. So in this situation, went significantly lower. Right now, utilization, which is average of demand, divided by average of capacity, is about 50%. Let's go and increase capacity of this one too. Copy it down. Numbers came down significantly. Averages came down to 2.76. Average inventory here is 1.39. Average inventory here is 1.37. And flow time came down to half a day. Now let's increase capacity, but not that much, but reduce variability. Therefore, instead of defining it as between 1 and 13, instead of doing it between 1 and 13, and the same for this station, instead of doing it like that, which leads to still a low flow time, 1.39, from half a day to 1.5 day, almost. But let's also reduce variability. Instead of having it with average of 7 between 1 and 13, let's have it between 6 and 8. Still has an average of 7, but with much less variability. You see, suddenly everything came lower as long as inventory is concerned. Let's do it for station 2 too. Okay, let's look at average inventory. Flow time is 0.2. A very low flow time. You see, and it is stable also. It's not very variable. Let's look at all the three scenarios once again. Okay, now here, flow time is about 1/5 of a day. Let's go to the original situation when capacity and demand were coming from 1 to 9. So flow time is about 16 days. 16 days, 19 days, 23 days, 10 days. Throughput and inventory are also there. Inventory sometimes on average was 112, 120. Then we increased the capacity from average of 5 to average of 10. As utilization goes down, waiting line goes down. So here, flow time is half a day. Average inventory is about 2.3. The last thing we did, we reduced the capacity from capacity of 10 to something around 7, but we did it from 6 to 8 with lower variability. See, the situation gets much better, and copy and control. Control C, Control C, Control V. And now we see while capacity is not that much, just because we reduced variability, average inventory has come to something around 1, and average flow time is something around 0.2. But we learned if demand and capacity are equal, waiting line can go significantly high. We can reduce utilization by increasing capacity. Of course, we don't want to reduce utilization by decreasing demand, but by increasing capacity. We can reduce the flow time, we can reduce the number of flow units in the waiting line, or instead of increasing capacity or increasing capacity too much, which is quite expensive, we may reduce variability and get the same results. Thank you very much for attending.